Okay, hello and welcome back to Chemistry Talk. Today we'll be continuing our discussion of acids and bases by determining the pH of strong acids and bases. So there will be another video for pH of weak acids and bases and pH of salts because the difficulty increases. So today will be a little bit more difficult than just your typical pH calculations because we're looking at strong acids and bases. So I just want to review how to calculate pH given you know certain things because you will need these skills in today's video. So as a review, a solution has a pOH of 9.2. Find the following. So the first thing I'm going to do is find the pH. And the pH would equal 14 minus the pOH. pOH here is 9.2. So the pH would equal 4.8. It's always good to start there, I would say. So if you have a pH less than 7, you have an acidic solution. So that answers that part. Now it's asking for the concentration of the hydrogen ions and the concentration of the hydroxide ion. Well, the pH equals the negative logarithm of the hydrogen ion concentration, and the pOH equals, let me fix that there. The pOH equals the negative log of the hydroxide ion concentration. Now we are solving for these concentrations. So what you need to do, as I discussed in the previous video, is you need to take the negative inverse of the log. You need to take the negative because you need to get rid of that negative to solve for the variable. You need to take the inverse to get rid of the log. So to do this, you're taking 10 to the negative x, x being your pH and your pOH. You're taking 10 to the x power because that is the inverse of the log. You're taking the negative to cancel out the negative in front of the log. So when you take the 10 to the negative of the 4.8 of the pH, you get a hydrogen ion concentration of 1.58 times 10 to the negative fifth molar. And when you do take 10 to the negative 9.2 to get the hydroxide ion concentration, you get 6.3 times 10 to the negative 10 molar. Now, important to note that in an acidic solution, your hydrogen ion concentration should always be greater than your hydroxide ion concentration, and that makes sense here. So you need these skills to calculate the pH of strong acids and bases. First example, a solution was prepared by dissolving a 0.3 grams of barium hydroxide in 100 mils of water. Density of water is 1.0, and that gives us the density of the solution. What's the pH of this solution? Okay, so we know we're dealing with strong acids and bases here. So barium hydroxide is a strong base. Its formula is BaOH2, so it's going to dissociate completely into barium ions, one barium ion, and two hydroxide ions. So if I want to calculate the pH of this solution, I first need to find the molarity of barium hydroxide in the solution. Then I can find the molarity of the hydroxide ion. Then I can find the pOH. Then I can find the pH. So it's going to be a multi-step problem here. So first thing to do is to calculate the molarity of barium hydroxide. So we're going to calculate the molarity of barium hydroxide, and molarity is moles over liters. To find the moles of barium hydroxide, I would divide the grams by the molar mass. And the molar mass of barium hydroxide is, let's see here, 71.3 grams. $171.3 grams, sorry, quick math there. So the molar mass is 171.3 grams. So to find the moles of barium hydroxide, you would divide the grams by the molar mass. And when you do that calculation, when you divide 0.30 divided by 171.3 to find the moles, you get 0.00175 moles of barium hydroxide. So that is the moles, 0.00175 moles. Remember, we're finding the molarity of the barium hydroxide. So now we need to find the liters of solution. Well, we have 0.3 mils of solution because it says 0.3 grams of barium hydroxide in 100 mils, so 0.3 mils of solution, but we also have the 100 grams of water. So the total mass of solution would be the 100 mils of water plus the 0.3 grams of solution. So we get, and the density of water is 1, so we get 100.3 grams of solution. And if you convert the grams of solution into liters, 1 milliliter per the density is 1.31 grams. And 1 mil, shouldn't put up the equal sign, 1 mil is 1,000 milliliters. 1 liter, rather, is 1,000 milliliters. So you get the liters of solution to be 0.07656 liters. So 0.07656 liters. Under the moles, you get the molarity of the solution to be 0.2288 molar barium hydroxide. So that is the first step here. So let me erase the extra, the work. So we're going to need more room. Sorry about this, just takes a while. Okay, so now that we have the molarity of the barium hydroxide, we can find the molarity of the hydroxide ion, because per 1 mole of barium hydroxide, you get 2 moles of hydroxide ions. So if we take the molarity of barium hydroxide and multiply it by 2, we get the concentration of the hydroxide ion concentration. So the molarity of the hydroxide ion concentration, 2 times the molarity of the solution, and we get that to be 0.0457 molar. Now we can find the pOH. The pOH equals the negative log of the OH concentration. The negative log of 0.0457 gives us our pOH, and our pOH equals 1.3. 14 minus the pOH will give us the pH. And the pH of this solution is 14 minus 1.3. So that would be 12.7. And that is our answer, the pH of the solution. So it's a strong base, so it makes sense that the pH is way above 7. So first we found the molarity of the hydroxide ion concentration. We found the pOH from the hydroxide ion concentration, and we found the pH. So a lot of steps here, but necessary steps. So here we are working with a strong acid. So the pH of a solution containing only hydrochloric acid is 1.1. What's the molar concentration of the hydrochloric acid? Assume that the density of solution is 1 gram per mil. So hydrochloric acid is a strong acid. It dissociates completely into hydrogen ions and chlorine ions. And what's contributing to the pH here is the hydrogen ion concentration. And the pH equals the negative log of the hydrogen ion concentration. Now, since it's a 1-to-1 ratio of acid to hydrogen ion, if we find the concentration of the hydrogen ion, that's going to be equal to the concentration of the acid because it dissociates 1-to-1. So the hydrogen ion concentration, remember, you have to take the negative log, the negative inverse of the log. So the negative inverse would equal 10 to the negative x, which would equal 10 to the negative pH, and the negative pH is negative 1.1. So you get your hydrogen ion concentration to be 0.079 molar. So since it's a 1-to-1 ratio, we can say that the HCl has a molar concentration of 0.079 molar. And that's the answer. Because HCl is a strong acid, dissociates in the hydrogen ions and chlorine ions, 1-to-1 ratio. The hydrogen ion is what's contributing to the pH of the acid. So the pH equals the negative log of the hydrogen ion concentration. If you want to solve for the hydrogen ion concentration, you need to take the inverse logarithm, the inverse negative logarithm, to get rid of the negative. So 10 to the negative pH, which is negative 1.1, gives us the hydrogen ion concentration of 0.079 molar. The hydrochloric acid will have the same molarity because it's a 1-to-1 ratio. So the molarity of the acid is 0.079 molar. Okay, last question here. How much sodium hydroxide in grams is needed to prepare 546 mils of a solution with a pH of 10? So sodium hydroxide is a strong base, why it would have a pH of over 7, and it will dissociate into sodium ion and hydroxide ion in solution. So if I have a pH of 10, I really want to know the pOH because that's what's contributing to the pH is the OH concentration here. So the pOH would equal 14 minus 10. So the pOH here is 4. Now if I want to know the concentration of hydroxide ion in solution, I need to solve for it using the equation, the negative log of the hydroxide ion concentration equals the pOH. So the pOH would equal the negative log of the hydroxide ion concentration. Call that X. So 10, once again, taking the negative log, the negative inverse logarithm. 10 to the negative fourth, well, that's just going to equal 1 times 10 to the negative fourth. And that's the molarity of the hydroxide ion concentration. From there, we can find how many grams of sodium hydroxide we need. If the molar concentration of hydroxide is 1 times 10 to the negative fourth, that means we need 1 times 10 to the negative fourth moles of sodium hydroxide per 1 liter of this solution. We have 546 mils of solution, or make this better here. I'm just going to convert this straight into liters. You could do the extra step, but you have 0.546 liters of solution, and per mole of sodium hydroxide is 40 grams. So the liters cancel, the moles cancel, and you're left with grams. So you need, with 3 significant figures, 2.18 times 10 to the negative third grams of sodium hydroxide. And that is your answer here, your final answer. So what we did, to recap, is we took the dissociation of sodium hydroxide, a strong base, into sodium ions, hydroxide ions. We're given the pH, so we wanted to find the pOH since the OH concentration is contributing to the pH. So the pOH would equal the negative log of the hydroxide ion concentration. We knew the pH, we needed the hydroxide ion concentration. We solved for the negative inverse, and we got 1 times 10 to the negative fourth molar of hydroxide ion. Or, since it's a 1-to-1 ratio, 1 times 10 to the negative fourth moles of sodium hydroxide per 1 liter of solution. That's the molarity. We took the liters of solution that we were given, canceled it, found the grams of sodium hydroxide using the molar mass, and we found the grams of sodium hydroxide. Hope this helped you to understand pH of strong acids and bases. Future videos will be doing pH of strong acids and of weak acids and bases, pH of salts, buffers, titrations, all that good stuff. And please be sure to subscribe and comment.